Hey guys, we are jumping into the next lesson in chemical reactions, and this lesson is going to be a little bit longer, so I apologize for that, but it's going to last you for 3 days. You won't hear from me again until Thursday with a new lesson. So we're going to practice a couple of different aspects of it each day. So there are 5 types of chemical reactions, and you have to be able to identify reactions as each of these types and also predict the products. So if I give you the reactants, then you can predict what the product would be. So let's go ahead and to jump into the first type of the equation. So the first type is a combination reaction, also referred to as a synthesis reaction. You'll want to write that down in your notes as well. I will use those terms interchangeably. They both describe the same thing. If you use either one, you'll get the full points for it. A combination or a synthesis reaction. So in a combination or a synthesis reaction, you have 2 substances that combine together to form a single substance. So for example, A plus B yields AB, and that would be a synthesis reaction or a combination reaction. So you see 2 examples here. Sulfur plus oxygen, that's a Hofbrinkel, so it has to be O2, comes together to yield sulfur dioxide. Now this one is already balanced. So there's 1 sulfur on the left, 2 oxygens on the right on each of those sides. Okay? For the next one, they had to add coefficients in to balance this one. But this one's potassium plus Cl2, because that's a Hofbrinkel, gives KCl. And then we've added these coefficients here to balance it, to give us 2 potassiums and 2 chlorines on each side of the equation. So let's practice a couple of these, okay? So in this first one, we have Al plus O2. So if we add aluminum and oxygen together, we are going to get aluminum oxide. Now, we can't just write AlO and be done, because that's not what aluminum oxide is. We still have to balance those charges and write it like we know that we should. So aluminum is a +3 charge, oxygen is a -2 charge. So when we crisscross those charges, aluminum oxide is written as Al2O3, okay? So now we have to balance the equation. So this first step was predict the product, and then you have to balance the equation, okay? So let's see, we've got aluminum and oxygen. Currently we have 1 aluminum on the left, 2 on the right, 2 oxygen on the left, and 3 oxygen on the right, okay? So let's see if we can, let's try to balance the aluminum first. So we'll put our 2 there, and that'll fix our aluminum problem, okay? But now we have to fix our oxygen problem. So if we put a 2 here, let's just go ahead and put this 2 here. So if we put a 2 there, that'll give us 6 oxygen, okay? But it also changes our aluminum to 4 aluminums, okay? And then if we put a 4 here, that'll give us 4 aluminums, okay? And then if we put a 3 here, that'll give us 6 oxygens. And so that would balance everything out properly. 4 Al, you can put those in. We'll talk more about that and how we use those more later. That would be your complete balanced equation. 4Al plus 3O2 yields 2Al2O3. So we have 4 aluminums and 6 oxygens on each side of the equation. And that's how we would balance this combination reaction. Okay? Let's look at the next one. Copper and sulfur. Okay? Now this one didn't really tell us what copper it is, so I'm just going to, let's pretend it's copper 2, and we'll just balance it with a sulfur 2. Okay? So let's call it a copper 2, and we'll just put it together and make sulfur. CuS, copper sulfide. Okay? Now, That one wasn't really a good example of a problem because it didn't tell you what the charge on that copper was. Now let's look at the next one. SO3, so that's a sulfate. Sulfate has a -2 charge. Double checking. Wait, nope. Sulfite, yes, sulfite has a -2 charge. Okay, and then, okay, so this is another one of those examples, like we talked about in class, where you want to. Now this last one's a little bit trickier. It is going to come together to form an acid. So it's going to be H2SO4, okay? And so now we have to balance it. So let's get here so we can balance. So we've got 2 H's on the left, 2 H's on the right, 1 S and 1 S, 4 O's and 4 O's, and it appears to be already balanced for us. Okay, so let's go ahead and let you try a couple. So you can push me on mute or pause, and you can work through these and then check them with me. So these were pretty easy. We've got beryllium oxide. Beryllium's a +2. Oxygen is a -2, so those canceled nicely. I forgot my coefficients to balance there. So if you put 2's in front of the beryllium and then the beryllium oxide, that will balance it. And then the last one makes sulfurous acid. It's a little bit different than sulfuric acid, but H2SO3, okay? So that's the first type of reaction, the synthesis reaction. The next one is a decomposition reaction. So in a decomposition reaction, it's the opposite of a synthesis reaction. We're taking an AB and breaking it down into an A plus B, okay? So you would recognize a decomposition reaction by just having one reactant. A synthesis reaction, you would have 2 reactants, okay? The A component and the B component. So let's look at these. CaCO3. So here you see heat and electricity. Those are not really reactants. I just couldn't write them over the arrow here in this. So CaCO3 is going to break down into CaO and CO2, okay? And that one looks like it's already balanced. The next one is water, and it's going to break down into hydrogen gas and oxygen gas, and I think that needs to be there to balance it. I think I missed that on your notes, so you'll want to fill that in there. So most decomposition reactions are going to require some type of energy source to break them down. So heat, light, electricity, so you will see that in most of your decomposition reactions. So that can be a clue as well. So let's look at this, PbO2 plus heat. So this is going to break down into Pb plus O2. Remember, this is a Hofbrinkel, so we have to keep that too, okay? And this appears to be balanced, okay? The next one, magnesium chloride, is going to break down to, I already gave you part of it here on this one, magnesium chloride plus oxygen. Okay, now we are going to have to balance this one. So to balance this, we will need a 3 here. And I think that balances everything else. Okay. Now, you pause me and you can try these for just a minute. So this first one is a little bit different. You have to put in what we started with. So we would have started with 2 HBr, which is hydrobromic acid. similar to hydrochloric acid. Any of those halogens you can call them hydrofluoric, hydrochloric, hydrobromic, hydroiodic acid. That's how you would say those. And add it to heat, and then you would get H2 and Br2. This one, okay, so you would have 4Ag plus O2, and then to balance it out, you have to add those coefficients in there. Okay? So that was the second type of reaction. So we've got the synthesis and the decomposition reaction. Okay? Now, the next one, single displacement reactions. So in a single displacement reaction, you have A plus BC yields AB plus C. Now, this starts to get just a little bit more complicated, okay? So for each of these, you're going to have one reactant that's by itself. It's a single element, okay? You're also going to have one reactant that's a compound or made up of two different elements, okay? Or two different ions. And then in the product, they switch. So this guy gets kicked out and left by himself. One of these do, okay? And then the other two pair up together. Now remember, your positive and negative charges are always going to have to pair together. So I'm going to show you just a little bit more about what I've got here. So let's look at this first example, okay? We've got a positively charged magnesium here. Our zinc is a positive 1, our nitrate's a negative 1, our magnesium is a positive 2, our nitrate's a negative 1, and our zinc is a positive 1, okay? So when we switch on this side, we still have to make sure that our positives and our negatives pair up together. You're never going to pair a positive and a positive or a negative and a negative. So what I'm trying to say is you couldn't switch it and have magnesium and zinc pair up together and leave nitrate out alone. It won't work like that. You have to make sure your positive and your negatives are going to pair together, okay? So we've got our magnesium nitrate, and this should have a 2 out here to balance the charge, okay? Sorry, that's not written correctly. And then the zinc is left, okay? And then you could go in and balance that. That would take a little bit of work to balance, but you could go in and balance that, okay? I'm not going to balance it right now. The next one, so we've got our positive, so it's going to pair up with the negative nitrate. Magnesium is going to pair with the negative nitrate and leave the positive silver left over, okay? And then in the last one, this one shows no reaction. And so sometimes it doesn't work. And I'm going to explain to you why. We have this diagram, which you will want to reference in single displacement reactions, which shows activity series, okay? If an element is lower on the list, it is not going to replace one that is higher on the list. So if this third one here, we're going to do a single displacement, what you would get would be MgNO3 plus lithium. Magnesium would basically displace lithium, okay? But if you look on here, magnesium is here on the list. Lithium is here on the list. So an element can't displace something that's higher than it. Magnesium cannot displace lithium, okay? Now, magnesium, here's magnesium again, it was able to displace zinc because zinc is down here beneath of it. It was also able to displace silver in the second equation because silver is beneath of it. But magnesium cannot displace lithium. So you have to look for that in these problems. Okay, this is only true for single displacement reaction when you have to look at the activity series, okay? I will not expect you to memorize this for a test, all right? For a test, I'm probably just going to say they are all going to displace if it's a single displacement reaction, okay? It's also important to note, sometimes you may see or hear these referred to as single replacement reactions. That's the same thing. It's just a different term, okay? But we have one element that's going to replace the second element in the compound in this type, okay? So let's practice a few of these. These are a little more challenging. I'm not going to balance them just for this right now, but you can go back and balance these later. You know how to do that, okay? So we've got zinc, which is our positively charged element, okay? Zinc is a +2, and I think I told you zinc was a plus. Yeah, zinc is a +2 here. I told you it was a +1. I'm sorry. Okay, so that probably changed. Maybe changed something. Maybe not. Okay. Anyway, back to this. Zinc is a +2. Okay, and it is. We need to see if it can replace this hydrogen. Okay, so let's look up here. Can zinc replace? Here's zinc. And here's hydrogen. So zinc can replace hydrogen, okay? So we're going to have zinc sulfate, and we're going to have hydrogen left over. Now, zinc is a +2, like I just said. Sulfate is a -3. So in order to write this correctly, okay, you would write it as such, okay, plus hydrogen. And then you can go in and balance that. All right. This next one, SN, so that's 10. And it's going to replace the other metal, which is sodium. So let's see if 10, here's 10, and sodium is right here. Can 10 replace sodium? It can't. So here you're going to say no reaction. Okay. The last one, we've got sodium plus HOH, which you may recognize as H2O. Sometimes I just think it's easier to see it written out as HOH. So can sodium replace hydrogen? That's what it would replace. Again, here's sodium. Hydrogen is down here. So it can replace hydrogen. So it's going to be sodium hydroxide plus H2. H is a Hofbrinkel, so it has to be H2. Okay? And that one appears to already be balanced. Okay? So pause me for a second. You can try a couple of these together. Okay, so it should look like this. Now this, to balance it, you will have to balance it like that. And I think both of those are balanced. So 2NaCl plus Br2 would be the first one. Chlorine is able to replace bromine. And in the next one, lead is able to replace iron if you double check on your activity series. So both of those had a reaction and are balanced now, I believe. Okay. So that's the third type of reaction, single displacement. Okay. The next type of reaction is a double displacement. So we don't have to worry about the activity series on this. That's only for single displacement reactions. In a double displacement reaction, or sometimes you'll see it referred to as a double replacement reaction. Okay? We have our elements that recombined, okay? So on the first side, AB is together and CD is together. And then on the second side, on their products, they've switched. So A has repaired up with D. The positive cation has repaired up with the negative anion. And then same thing, C, the positive cation, has repaired up with B, the negative anion. So you have to make sure that you do it that way, okay? A first element in the compound is always going to pair with the second element in the compound because you have to keep those charges balanced. And you can't do that if they're both positives or they're both negatives. So we have an exchange of positive ions between two reacting compounds, okay? Or an exchange of negative ions, if you prefer to see it that way, between two reacting compounds. Usually, these produce a precipitate. So we'll talk about that more on Thursday, what that means. A precipitate is something that doesn't dissolve in water. It's something that like floats to the top or precipitates out, okay? Sometimes water and gas can be produced in these as well. So let's look at some examples, okay? Sodium and sulfur and cadmium and nitrate. Okay, so sodium is going to repair, the first one is going to repair with this one, the second piece. So we should have sodium nitrate. And then what's left, cadmium, is going to repair with sulfur, cadmium sulfur. And you could write these in either direction. If you wrote cadmium sulfur second and sodium nitrate first, that's perfectly fine. Okay. On the second one, calcium is going to pair up with chlorine, our first piece and our second piece, to get calcium chloride. And then OH is going to pair up with H to give us HOH or water. Okay? And again, you could switch the order of those as well. Okay? And you still have to balance the charges. So when we paired up calcium and chlorine, calcium was a positive 2. So we had to put the 2 here on chlorine to balance those charges. Okay? So hopefully you're seeing how all of this stuff is starting to really connect together and why we had to be really good at being able to name compounds. That's critical to being able to move on to this. Okay? So let's look at a couple together. So we want to complete these equations and then balance them if we can, okay? So we have Na. We want to put it with a second term. So it should be NaSO4, okay? Now, sulfate is a -3 charge. Sodium is a +1 charge. So we're going to have to make it Na3SO4, okay? And then, I should have made that a box. Sorry, if I'm trying to keep things visual here. H is going to go with Cn. Okay, we always want to write our positive charged cation and our positive charge first and our negative charge second when we write these. Okay, that's the way we write compounds. We got a +1 charged H, a -1 charged Cn, so that is done correctly. Okay, now you can go back then and balance this if need to. Okay, and I'm not going to do that step just for the length of this video. The next one, you have the barium is going to go with the carbonate. Carbonate is, make sure, I think it's a -2 charge. I'm going to say it's a -2 charge. Barium's a +2 charge, so that's fine. And then that's going to leave our K to go with the Cl. And that's a positive one and a negative charge, so they're good. And then you can go back and balance those, okay? So you can pause me, and I want you to try a couple of these on your own, and then you can come back and check. Now, I want you to pay attention on these. This has got some important stuff in it. So, in this one, you would get iron chloride together and hydrogen sulfide together, okay? Now, I want you to really clue into this piece. I'm going to guess that many of you did not put Cl2 there. If you did, you were all over it, okay? But I'm going to guess that many of you didn't. So, we have to make sure that the charges are still balanced, okay? Iron, it doesn't tell us what the charge of iron is, but we know when it's paired up with sulfur, it's in a 1-to-1 ratio here. Neither of them have subscripts. So that means it's going to have the same charge as sulfur did. So this is an iron 2 then, okay, because sulfur is a -2. So in order to balance that charge, you had to put the 2 on chlorine, okay? That's really important. We see the same thing down here on the bottom with this one. So we have iron again. Again, iron's a transition metal. We don't know what the charge is. But when it's put with nitrate, which is a -1 charge, they had to have 3 nitrates. Okay? So that means that this iron is an iron plus 3. Okay? So then when we move it over here on the other side of our reaction, when we predict the product, we are going to have 3 hydroxides to balance that iron, okay? So make sure you've written your chemicals correctly. And then you can go back and balance this reaction later if you wish. You don't have to balance them all in your notes for the sake of doing that today, but that is one of your assignments later this week as we go forward, okay? Now, the last type of reaction, finally, is the combustion reaction, okay? So the combustion reaction is going to be, it's got a specific equation too, okay? It's got the formula X plus O2 yields CO2 plus H2O, okay? Or it's always got to have, many times you'll see it like that, okay? Not always, but it always has to have O2 as a reactant. If you see O2 as a reactant, it's a pretty good chance that it's a combustion reaction, okay? So it's going to react with oxygen and produce energy as heat and light. So when it's complete, carbon dioxide and water are the only products. So you see here we've got an incomplete reaction. It doesn't have only carbon dioxide and water. Here is going to be a more complete reaction that's got only carbon dioxide and water. And in that one, you see that it follows this formula. It's got X plus O2 yields CO2 and H2O, okay? So that's pretty typical of a combustion reaction. So let's look at a few examples. Okay, so let's try a couple here on our own. So these, they have given us the reactant, all that we've got to react with. And so you're going to recognize these a lot of times because they have C and H and sometimes O, okay? And so we're going to react it with oxygen, and it's going to give us CO2 plus H2O, okay? And then you can go back and balance that, all right? The next one, they've given us something that looks a little bit different. You could rewrite it as like H2CO2, or you can just leave it the way that it is. It doesn't matter either way. But we're going to add O2 to it, and give us CO2 plus H2O. Okay? And that's a simple combustion reaction. Let me let you try a couple of these on your own. Okay? So you can pause me and you can try them. Now, this second one, some of you may recognize as the equation for cellular respiration, or if you flip it around backwards, it would be the equation for photosynthesis. Okay, and so both of these, all you have to do is add oxygen, and then it's going to give CO2 and H2O for both of them. I went in and added the 6 as coefficients and balanced this one because I knew that one in my head. But you can go back and balance the other ones as well as you want if you wish. Okay? So that's how you would do that one.